this is the lecture 6.2.2 on our course, and now we will be essentially repeating the same calculation as done earlier, but now for the electron vacancy states, so holes in the valence band. So we want to calculate the density of vacancy states in the valence band in this lecture, and this is what we will be doing. I don't go much more into the motivation. We already know what we want to achieve, and basically we already also know how to achieve that. So we ended our previous lecture with this quite classical picture, and now we are repeating the same kind of calculation as before, but not now done at an electron state in the conduction band, but rather for a vacancy state, so a kind of like a one missing electron and the valence band, and we want to calculate the density of states for these kind of creatures, so that we would then be able to estimate what would be the electrical conductivity based on these kind of vacancy states. So we will repeat the earlier calculation, but now we do it for an electron vacancy, and these are also known as holes. And these reside in the valence band, so not in the conduction band, but rather in the valence band. And effectively, their movement, or maybe I should say that the kind of movement of the surrounding electron states can give rise to a macroscopic formation of current. So this is analogous to the case of having some electrons at the conduction band that is not full. That gives rise to a macroscopic conductivity. So essentially the same thing happens, but now for vacancy states in the valence band. And similarly to the earlier, like we have now a energy value in the valence band, energy value EV, that is the highest energy value we have for the valence band. So this is analogous to the case of EC, the smallest energy value we have associated with the conduction band, but now we must treat the highest energy, so in order to land us in the same kind of location in our band diagram. So we must take use of these EV value because that provides us the kind of integration limits, and this is then how we get started. So we want to know the density of holes, so P will be the parameter that we will be calculating, and this is the value that is associated with valence band. And the associated electronic density of states, or maybe I should just say it's a density of holes, we term that as a GH parameter, and that of course depends on the energy. And as before, we are interested in dealing with moderate temperatures, so we must apply also the Fermi-Dirac statistics on our situation. So we are dealing in a way electrons, so how an electron is being missing from a given state. So we must deal with fermionic particles. And the Fermi-Dirac distribution now, Fe, would give us the probability that an electron would be in a specified excited state. So please note the labeling here. So we have Fe here, and this is really just a Fermi-Dirac distribution for a electron. So we are not yet saying that this is the Fermi-Dirac of a hole, but rather the Fermi-Dirac distribution associated with a hole state, that would be the complement of this Fermi-Dirac distribution. And this complement gives us then the probability of having a hole in a specified state. So the actual Fermi-Dirac distribution we must calculate and use would be the FH, and that depends of course on the energy and temperatures, and this is the complement of the electron probability of being in that state. So 1 minus Fe. Because together, of course, when we would move the Fe term to the left-hand side, that would physically tell us that physically, of course, the state must either be filled with an electron or it won't be filled with an electron. So essentially, another way of saying it, the electron must be somewhere in the system, and we cannot avoid that fact. And this is a plain, simple physical restriction we have in the system. A single electron, we know that we have many electrons in the system, and all of them must be somewhere, and then this allows us to have tools to calculate actually the probability distribution associated with the whole state. It's quite simple stuff in the end, but maybe you need to think this through yourself before you see it, what I was meaning. And now we're left with a similar looking equation, an integral that we had earlier, but now we are just calculating the density of states for holes or concentration of holes, so P, and we have 1 over V. We are still considering a cubic cubic volume of a material that has a side length of L, so V is L cubed, and then we are now integrating all over from minus infinity energies up until EV value. Please remember the figure. So what is the meaning of EV, so that you understand why the integration limits are like this. And then we have the whole density of states, so GH, and then we have the whole Fermi-Dirac distribution, so FH. And then of course we are integrating with respect to energy. And we can already make the insertion, so we just replace that whole Fermi-Dirac distribution with the complement, so that we can now actually like calculate this Fe. So this is how our integral is being transformed into. And as before, let's first focus on the Fermi-Dirac distribution. That's maybe the easier term to figure out. And we just note that the 1 over Fe, that is of a form that we have 1 minus 1 over Ex plus 1. That's the functional form. So of course, like we can multiply, we can turn that unity here to be of a similar looking term, so that we would have then like Ex plus 1 both on the numerator and denominator, and then we can simplify things. So essentially what I mean here is that we can transform our 1 to be an exponent minus x plus 1, and in the denominator we will have exponent minus x plus 1. So this is still unity, right? Nothing changes. And then we will change our earlier exponent by making an exponent minus x to be a common multiplier. And then of course in the denominator we will change things accordingly. So we will just change unity to be then minus x. Sorry, unity we changed it to be exponent minus x, and then the earlier exponent x is being transformed into unity. So what we have here, what now happens is that this is being equal to this, and we have minus sign here, so they vanish. So what's left in the numerator is that we have unity, and then in the denominator we have exponent minus x plus 1. And then again, we assume that we are dealing with moderate temperatures, so that then this chemical potential minus energy and negative of that is far larger than the kPt value. And then in essence, what we get is that this minus 1 minus Fe is approximately exponent mu minus Ek Ek per kPt. So this is then what we approximate things to be. And this helps us to get a slightly cleaner equations out. So now what we are left with is that we must then estimate the whole density of states, so this GH term. And again, we assume that we are dealing with a parabolic valence band, so that the dispersion relation is of a form, so that we have the Ek depending on the amplitude of the wave vector, and we have the EV value minus h bar squared k squared divided by 2 times the effective mass of our vacancy state, so mh star. Here, this is the effective mass of a hole, and of course this depends on the curvature of the valence band. And please note what this tells us, that when we have a k equals 0, this kinetic term vanishes and we are left with the EV value. And this is certainly the case when we are looking at the band dispersion and band diagram, that when we have a 0k value, then the valence band has its highest value, and then it's a parabolic pointing downwards. And now we can insert this into our equation, and we can calculate what is the density of states. So as before, the density of states is still being defined, that it's the derivative of a function of n with respect to the energy. And I don't do the calculation here, but essentially the density of states of holes gets a very similar form as before for the electrons in the conduction band. So this is of the form V over 2 pi squared. Then we multiply this with 2 times m star h. So this is the effective mass of the hole divided by h bar squared, and this to the power of 3 over 2. And then we have the energy term that looks like a square root functional dependence on the energy. So we have EV minus the dispersion relation E, the energy associated with the given state associated with the given wave vector amplitude k. This is inside the square root. And now we can calculate the original integral, and I do not repeat the calculation anymore. It's exactly the same kind of integral calculation as we did in the previous lecture, and then we're left with the final outcome that we have 1 over square root of 2. Then we have the m star h times kBt per pi per h bar squared to the power of 3 over 2, and then we have the exponent form. So we have exponent EV minus chemical potential nu per kBt. And again, we can simplify the notation slightly so that we take the first multiplier that does have a slight temperature dependence, and then we transform this into a new variable, so NF, V, and then we have the final exponential temperature dependence, where we also have the dependence on the chemical potential. So this is the functional form, and this is the result, and this already provides us an information of how many vacancy states we have in the valence band. So all in all, what we see that since we did assume that we are at moderate temperatures, and that's where we are like working with our math, is that the number or density of holes in the valence band is given by this kind of quite simple relation. But please note that this effective parameter in the beginning, this does depend, of course, on the effective mass. So depending on the kind of like curvature of the valence band, this constant here, this amplitude here would change accordingly. So this is still an approximation assumption we have made. And this also depends slightly on the temperature, so don't be fooled by the notation here, so that it does not only have dependence on the effective mass of the vacancies, but also on the temperature. And here, of course, we have the exponential form that depends on the chemical potential. So, of course, depending on the kind of bandwidth, the energy bandgap value that we have for the semiconductor, this will change accordingly. And of course, when we change the temperature of our semiconductor, this term will dramatically change. And this is the kind of provides us an understanding how semiconductors have that kind of electrical conductivity that usually increases when we increase the temperature of our semiconductor. And this is a behavior that is quite different when we would compare the behavior of semiconductors against metals, because when we heat up a metal, then usually the electrical conductivity of a metal decreases because we start having more effects from the impurities and scattering of electrons. But all in all, please note the curvature of the band is really important, so that we are approximating things, we are assuming things, but in real life, like this actual band shape here, it's actually quite important. So please remember of this. And it's really coming by, like boiling down to the effective mass of our state that is being affected when we change the curvature. And in this picture, you can see that there are these kind of possibilities of having so-called light holes and then heavy holes. And then you can see the curvature really matters. And that's the kind of physics that we will be dealing with when we're dealing with the semiconductors. So this is all I had to say. So this was a quick and dirty derivation of the kind of density of holes in the valence band, but now we have it, and now we would already have tools to estimate the electrical conductivities of intrinsic semiconductors. So these are actually quite useful bits of equations that we have already derived. So I thank you for your time and patience, and please join me soon for the next lecture, where we will be covering a so-called law of mass action, because that's also very fundamental in terms of understanding the electronic properties of semiconductors. But more on that, of course, in the next lecture. So please, thanks for this one, and please stay tuned. Thanks and bye-bye.